Hey everybody, this is Lindsay. My final research presentation is centered around microbial food cultures and the microbes that are found currently in food, the non pathogenic microbes that are currently found in food. So think production, not spoilage. Microbial food cultures and my research, I found that they're not legally defined. They're commonly referred to as live bacteria, yeasts, or molds used in food production, but there is a not necessarily an actual defined use of microbial food cultures that you'd find in Merriam-Webster's dictionary, for instance. The cultures included, but are not limited to starter cultures, dairy starter, yogurt starter, anything that is going to be a microbe based booster or food producer. So you think about when we did our milk to yogurt lab, you think about anything like a sourdough starter. People keep those alive for hundreds of years. Any of the cured meats that can stay out at room temperature, wine, beer, etc. Those are likely a microbial food culture. They are abbreviated as MFCs, and MFCs contribute to one or multiple unique properties of food, especially regarding flavor, color, texture, wholesomeness, health, and nutritional benefits and food safety. So, if you see anything that's been fortified, a lot of times they're utilizing microbial food cultures to do that. So, think of cereals, think of baby food, think of yogurts. If anything has been fortified, there's a really good chance that microbial food cultures are somewhere included in this process. And as of 2012, the inventory of MFCs contains 195 bacterial species and 69 species of yeasts and molds. Microbial food cultures are categorized and um, kept up with so that they can be regulated by the FDA, more or less, and other global food regulatory departments. Anything that goes in food needs to be traced and tracked and um, kept aware so that it can be traced back, worst case scenario. So there's a catalog of MFCs. Little refresher on some microbes. We covered this during our food microbiology portions. But one of the starter cultures that you'll hear pretty commonly or read about pretty commonly are the Lactococcus bacteria family. It's a sphere shaped gram positive bacteria with 12 species that are currently recognized. It was first isolated from green plants, and several of the Lactococcus strains are used in the early stages of production of many cheeses. For instance, Lactococcus lactis or Lactococcus lactis with the subspecies Cremoris. It will convert lactose into lactic acid. Another starter culture that's likely a refresher is the Streptococcus bacteria. It's a sphere shaped gram positive bacteria with over 50 species currently recognized. Streptococcus is important in the production of fermented milks, yogurt, feta, and mozzarella cheeses. And the Streptococcus thermoplalis is the second most commercially important starter culture. This has been diverged from its pathogenic relatives to occupy the ecological niche of milk. So it's not going to give you strep throat by um, drinking it in milk because it is diverged from the bad part of strep. Another starter culture is lactobacillus. Lactobacillus is very, very common. Pretty sure lactobacillus is what is often advertised when it comes to Activia or any other kinds of yogurt that you might see commercials for. It's a rod shaped gram positive bacteria with over 50 species also currently recognized. And Lactobacillus plantarum is found in sourdough and cereal based fermented products. Lactobacillus paracasei is found in matured cheese, along with Lactobacillus curvatus, casei, and rhamnosus. And Lactobacillus rhamnosus accelerates cheese ripening and also improves cheese flavor. The next one is the propionic acid bacteria. It's a rod shaped gram positive bacteria. And then the Propionibacter shermani digests acetic acid and converts it into propionic acid, acetate, and CO2. CO2 is what gives cheese its holes. So if you have Swiss cheese, likely propionic acid has been included in the production. Products of fermentation contribute to nutty and sweet flavors of cheese, and its performance and growth is highly dependent on the presence of the Lactobacillus helveticus, so they're often partnered up when it comes to production. Yeast is another microbe commonly found in food. This is the Saccharomyces family. It's an ellipsoid shaped and can either be gram positive or gram negative depending on the maturity of the plate when viewed. Saccharomyces cerevisiae, also known as baker's yeast or brewer's yeast, is found in bread, beer, and is the main source of nutritional yeast. For my non-vegan friends and my non-vegetarian friends, or dairy-free, nutritional yeast is used in a lot of recipes that when you're trying to replicate cheese. So it's literally yellow flakes and it tastes like cheddar. Saccharomyces bayanus is used in winemaking and cider fermentation, and entire colonies can grow rapidly and mature in only 3 days. So it's a very quick growing microbe. Microorganisms are historically consumed by humans. You've probably eaten some today. You will see all of the fungi and yeasts responsible for cheese, tempeh, bread, beer, and wine. Sometimes you need both bacteria and yeast. For instance, if you're going to do kombucha, or then just straight up bacteria for when it comes to the fermented soybeans, kimchi, the salted fermented seafood, yogurt, and cheese. So lots of different microorganisms might exist in your meals throughout the day. This leads me to discussing the potential future of microbes in food. So precision fermentation is a market that is currently being explored and invested in. It is a growing market with a vast difference between today and 2022, with about 1.6 billion investment dollars or investment assets in the market. It's expected to grow to about 36.3 billion by 2030. So just 8 years from now, 7 years from now, depending on data publication, it is projected to account for that 36.3 billion. So it's growing very, very quickly. And this is specifically in the Asia Pacific market, the rise in demand for plant based food and beverages due to increasing health awareness, or even global forecasts and potential climate awareness as well. So, precision fermentation, I'll touch on a little bit more on what that is on this next slide here. So, fermentation is commonly used on, you've likely had fermented foods in the past. There is traditional fermentation, which is the process of changing a food through microbial and aerobic digestion. So if you've had fermented pickles, or I guess it'd be fermented cucumbers, or if you have had kombucha or, wine, beer, etc., it is a ingredient that has been fermented alongside the use of microbes. We have biomass fermentation, which uses the high protein content and rapid growth of microorganisms to efficiently make large amounts of protein-rich food. So, for instance, the yeasts would be very beneficial at this point because they are rapid growing microorganisms. And then precision fermentation, which is what I touched on the last slide, it uses microorganisms to produce specific functional ingredients. So if you're looking today, for instance, at Quorn, Quorn, it's a brand of alternative plant-based meats. They are already using precision fermentation, and they have a completely different standalone protein that is the substitute. So rather than a black bean patty where you're going to get protein from the black beans, or something that's chickpea based, and so you're not taking protein rich plant based foods and turning it into a patty of some sort, it's a completely different standalone product that has been precision fermented from microbes. And it is potentially the future of food, particularly if you think about the ecological footprint involved with farming, or when it comes to CO2 emissions or land use. It would be nice to have a warehouse that just had a bunch of tanks in it and could produce a protein that has the same, if not more, grams per uh, gram of food versus the space and the CO2 emissions needed for functional wide scale farming. As I touched on a little bit, this is important because we're about to get real crowded. The world population growth between 1700s and the 2100s is expected to hit 10.9 billion humans on the planet. Um, that's more people than we currently have the infrastructure and the space to feed. So, if we aren't able to get ahead of this and start to try things like precision fermentation and figure out how we can produce food through the use of lab techniques versus straight up farming, we could potentially be in a little bit of a scary place by 2050 is the first red flag. There's an actual doomsday counter counting down to 2050, so that'll help you sleep at night about the potential lack of food and the loss of food. I guess increasing scarcity of food. Another reason why this is important is due to climate change, and things are potentially going to get a lot wetter, but also a lot drier. So, when you have drought and severe drought for a long period of time, you're more likely to have flooding when the rain finally does come. Both droughts and floods are equally as bad for farmland and production of food. This is two different scenarios. The top row is the worst of the two cases of scenarios between 2030 and 2090. And then the bottom row is talking about what would happen if it was to be less intense of an event. You'll see the same top row, bottom row on this slide here when it talks to the number of days over 90 degrees. This is about two different climate change scenarios again. And there will be many more 90-degree days, even with the less terrible scenario in the important farm states like Iowa, Missouri, Kansas. I know a lot of places have Texas on there too. We do a lot of cattle down here. There's a bunch of beef in this state. And the hotter the days get, the harder it will be to not only keep the livestock alive at these times, but things will start to get more expensive, and their food that comes from the plants that might be affected by the droughts and the flooding from the previous slide are also going to get more scarce. And so coming up with an alternative food production method is kind of a forefront right now of microbiological research, just due to the potential looming crisis on the horizon again. Sweet dreams. So, some conclusions. We interact and eat microbes every day, basically. I kind of feel like you're either eating them on purpose or you're eating them from the air, regardless. So, knowing which ones are the good ones and get your food doing what you want it to do is beneficial. And even more so, knowing which microbes could be produced and turned into genetically modified or synthetically produced food or food ingredients or powders or supplements is very important for when it comes to sustainability and long-term life and existence on this planet as we become more and more populated at the same time experience harsher and more alarming climate scenarios that will be playing out within the next few years. So I feel like precision fermentation is definitely a future of food. Hopefully this has piqued your interest. There are a ton of references listed on the next slide if you want to pause it and take a look at a few and get a feel for where I got some of my information. But my hope is that I pique your interest and you are willing to try some precision fermented food.